Hello. Welcome to the 8th module of the Python Fundamentals course. Here we'll cover classes, Python's tools for creating new types. You can get a long way in Python using the built-in scalar and collections types. For many problems, the built-in types and those available in the Python standard library are completely sufficient. Sometimes, though, they aren't quite what's required, and the ability to create custom types is where classes come in. As we've seen, all objects in Python have a type, and when we report that type using the type built-in function, the result is couched in terms of the class. Classes are a means of defining the structure and behavior of objects at the time we create the object. Generally speaking, the type of an object is fixed throughout its lifetime. As such, classes act as a sort of template or pattern according to which new objects are constructed. The class of an object controls its initialization and which attributes and methods are available through the object. For example, on a string object, the methods we can use on that object, such as split, are defined in the str class. Classes are a key piece of machinery for object-oriented programming, and although it's often true that OOP is useful for making complex problems more tractable, it also commonly has the effect of making the solution to simpler problems unnecessarily complex. A great thing about Python is that it's highly object-oriented without forcing you to deal with classes until you really need them. This sets the language starkly apart from Java and C#. Python gives us the tools to define new classes, which can be completely novel or based on existing classes. Class definitions are introduced by the class keyword followed by the class name. By convention, the new class name in Python uses camel case, sometimes known as Pascal case, with a capital letter for each and every component word. Since classes are awkward to define at the REPL, we'll be using a Python module file to hold our class definitions. Let's start with the very simplest class, to which we'll progressively add features. For this module, I'll be using the PyCharm Python IDE so that it's easy to follow the code examples and their use in the REPL. In this example, we'll model a passenger aircraft flight between two airports by putting this code into airtravel.py. The class statement introduces a new block, so we indent on the next line. Empty blocks aren't allowed, so the simplest possible class needs at least a do-nothing pass statement to be syntactically admissible. Just as with def for defining functions, class is a statement that can occur anywhere in a program and which binds a class definition to a class name. When the top-level code in the air travel module is executed, the class will be defined. We can now import our new class into the REPL and try it out. The thing we've just imported is the class object. Everything is an object in Python, and classes are no exception. To use this class to mint a new object, we call its constructor, which is done by calling the class, as we would a function. The constructor returns a new object, which here we assign to a name f. If we use the type function to request the type of f, we see that it's of class airtravel.flight. The type of f literally is the class. Let's make our class a little more interesting by adding a so-called instance method, which returns the flight number. Methods are just functions defined within the class, and instance methods are functions which can be called on objects, or instances, of our class, such as f. Instance methods must accept a reference to the instance on which the method was called as the first argument, and by convention this argument is always called self. We have no way of configuring the flight number value yet, so we'll just return a constant string. Now from a fresh REPL, let's import that and see how it works. Notice that when we call the method, we do not provide the instance f for the actual argument self in the argument list. That's because the standard method invocation form with the dot is simply syntactic sugar for the class name, followed by a dot, followed by the method name with the instance passed as the first argument. If you try the latter, you'll find that it works as expected, although you'll almost never see this form used for real. This class isn't very useful because it can only represent one particular flight. We need to make the flight number configurable at the point that flight is created. To do that, we need to write an initialization method. If provided, the initialization method is called as part of the process of creating a new object when we call the constructor. The initializer method must be called _init, delimited by the double underscores used for Python runtime machinery. Like all other instance methods, the first argument to _init must be self. In this case, we also pass a second argument to _init, which is the flight number. The initializer should not return anything, it simply modifies the object referred to by self. If you're coming from a Java, C# or C++ background, it's tempting to think of double_init as being the constructor. This isn't quite accurate. In Python, the purpose of double_init is to configure an object that already exists by the time it's called. The self argument is, however, analogous to this in Java, C# or C++. In Python, the actual constructor is provided by the Python runtime system, and one of the things it does is check for the existence of an instance initializer and call it when present. Within the initializer, we assign to an attribute of the newly created instance called _number. Assigning to an object attribute that doesn't yet exist is sufficient to bring it into being. Just as we don't need to declare variables until we create them, neither do we need to declare object attributes before we create them. We choose _number with the leading underscore for two reasons. First, because it avoids a name clash with the method of the same name. Methods are functions, functions are objects, and these functions are bound to attributes of the object, so we already have an attribute called number, and we don't want to replace it. Second, there is a widely followed convention that the implementation details of objects which are not intended for consumption or manipulation by clients of the object should be prefixed with an underscore. We also modify our number method to access the _number attribute and return it. Any arguments passed to the flight constructor will be forwarded to the initializer, so to create and configure our flight object, we can now do this. We can also directly access the implementation details. Although this is not recommended for production code, it's very handy for debugging and early testing. If you're coming from a bondage and discipline language like Java or C# with public, private, and protected access modifiers, Python's everything is public approach can seem excessively open-minded. The prevailing culture among Pythonistas is that we're all consenting adults here. In practice, the leading underscore convention has proven sufficient protection even in large and complex Python systems we have worked with. People know not to use these attributes directly, and in fact they tend not to. Like so many doctrines, lack of access modifiers is a much bigger problem in theory than in practice. It's good practice for the initializer of an object to establish so-called class invariants. The invariants are truths about the objects of that class that should endure for the lifetime of the object. One such invariant for flights is that the flight number always begins with an uppercase two-letter airline code followed by a 3 or 4-digit route number. In Python, we establish class invariants in the double_init method and raise exceptions if they can't be attained. We use string slicing and various methods of the string class to perform validation. For the first time in this course, we also see the logical negation operator, not. Ad hoc testing in the REPL is a very effective technique during development. If we construct a flight with a valid flight number, everything works as expected. However, if that flight number doesn't have an airline code, we get a value error. Likewise, if the airline code is lowercase, we get a value error. And if we construct a flight that has letters instead of numbers, we get another value error. And if we try to use 5 numbers instead of 4, we also get a value error. Now that we're sure of having a valid flight number, we'll add a second method to return just the airline code. Once the class invariants have been established, most query methods can be very simple. One of the things we'd like to do with our flight is accept seat bookings. To do that, we need to know the seating layout, and for that we need to know the type of aircraft. Let's make another class to model different kinds of aircraft. The initializer creates 4 attributes for the aircraft: registration number, a model name, the number of rows of seats, and the number of seats per row. In a production code scenario, we would validate these arguments to ensure, for example, that the number of rows was not negative. This is straightforward enough, but for the seating plan, we'd like something a little more in line with our booking system. Rows in aircraft are numbered from 1, and the seats within each row are designated with letters from an alphabet which omits I to avoid confusion with 1. We'll add a seating plan method which returns the allowed rows and seats as tuples containing a range object and a string of seat letters. It's worth pausing for a second to make sure you understand how this function works. The range call produces an iterable sequence of row numbers up to the number of rows in the plane. The string and its slice method return a string with 1 character per seat. These two objects, the range and the string, are bundled up into a tuple. With that in mind, let's construct a plane. See how we use keyword arguments for the rows and seats for documentary purposes. Also recall that ranges are half open, so 23 is intentionally one beyond the end of the range. The law of Demeter is an object-oriented design principle that says you should never call methods on objects you receive from other calls. Or, put another way, only talk to your friends. We'll modify our flight class to accept an aircraft object when it's constructed. And we'll follow the law of Demeter by adding a method to report the aircraft model. This method will delegate to aircraft on behalf of the client rather than allowing the client to reach through the flight and interrogate the aircraft object directly. We also add a docstring to the class. These work just like function and module docstrings. We can now construct a flight with a specific aircraft. Notice that we construct the aircraft object and directly pass it to the flight constructor without needing an intermediate named reference for it. Complex is better than complicated. Many moving parts, combined in a clever box, are now one good tool. The aircraft model method is an example of complex is better than complicated. The flight class is more complex, that is, it contains additional code to drill down through the aircraft reference to find the model. However, all clients of flight can now be less complicated. None of them need to know about the aircraft class, dramatically simplifying the system. First, we'll perform a small refactoring and extract the seat designator parsing and validation logic into its own method, parseSeat. We use a leading underscore here because this method is an implementation detail. The new parseSeat method returns a tuple with an integer row number and a seat letter string. This leaves allocateSeat much simpler. See the call to parseSeat and notice that method calls within the same object also require explicit qualification with the self prefix. Now we've laid the groundwork for our relocatePassenger method. This parses and validates the FromSeat and ToSeat arguments and then moves the passenger to the new location. It's also getting tiresome recreating the flight object each time, so we'll add a module-level convenience function for that too. It's quite normal to mix related functions and classes in the same module. Now let's see that at the REPL. You may find it remarkable that we have access to the flight class when we have only imported a function, makeFlight. This is quite normal, and it's a powerful aspect of Python's dynamic type system that allows us this very loose coupling between code. Let's go on and move Guido back to row 15 with his fellow Europeans. It's important during booking to know how many seats are available. To this end, we'll write a numAvailableSeats method. This is achieved using two nested generator expressions. The outer expression filters for all rows which are not none. This excludes our dummy first row. The value of each item in the outer expression is the sum of the number of none values in each row. This inner expression iterates over values of the dictionary and adds 1 for each none found. See how we split the outer expression over 3 lines to improve readability. And just to check, let's do a little bit of math.
Now we'll show how it's quite possible to write nice object-oriented code without needing classes. We have a requirement to produce boarding cards for our passengers in alphabetical order. However, we realize that the flight class is probably not a good home for details of printing boarding passes. We could go ahead and create a boarding card printer class, but that's probably overkill. Remember that functions are objects too, and are perfectly sufficient for many cases. Don't feel compelled to make classes and objects without good reason. Rather than have a card printer query all the passenger details from the flight, we'll follow the object-oriented design principle of tell, don't ask, and have the flight tell a simple card printing function what to do. First, the card printer, which is just a module-level function. The new Python feature here is the use of line continuation / characters, which allows us to split a long statement over several lines. This is used, together with implicit string concatenation of adjacent strings, to produce one long string with no line breaks. We then measure the length of this output line, build some banners and borders around it, and then concatenate the lines together using the join method called on a new line separator before printing the whole card followed by a blank line. Note that the card printer doesn't know anything about flights or aircraft. It's very loosely coupled. You can probably easily envisage an HTML card printer that has the same interface. To the flight class, we add a new method, makeBoardingCards, which accepts a card printer. This tells the card printer to print each passenger, having sorted a list of passenger seat tuples obtained from an _passenger seats implementation detail method. Note the leading underscore. That method is in fact a generator function which searches all seats for occupants, yielding the passenger and the seat number as they are found. Now, if we run this on the REPL, we can see that the new boarding card printing system works.
Polymorphism is a programming language feature which allows us to use objects of different types through a uniform interface. The concept of polymorphism applies to functions and more complex objects. We've just seen an example of polymorphism with the card printing example. The makeBoardingCard method didn't need to know about an actual, or as we say, concrete, card printing type, only the abstract details of its interface, essentially just the order of its arguments. Replacing our console card printer with the putative HTML card printer would exercise polymorphism. Polymorphism in Python is achieved through duck typing. Duck typing is in turn named after the duck test attributed to James Riley, the American poet. Quote, "When I see a bird that walks like a duck and swims like a duck and quacks like a duck, I call that bird a duck." Duck typing, where an object's fitness for a particular use is only determined at runtime, is the cornerstone of Python's object system. This is in contrast to statically typed languages, where a compiler determines if an object can be used. And in particular, it means that an object's suitability is not based on inheritance hierarchies, base classes, or anything except the attributes an object has at the time of use. Let's return to our aircraft class. The design of this class is somewhat flawed, in that objects instantiated using it depend on being supplied with a seating configuration that matches the aircraft model, which for the purposes of this exercise we assume is fixed per model. Better and simpler perhaps to get rid of the aircraft class entirely and make separate classes for each specific model of aircraft with a fixed seating configuration. Here's an Airbus A319. And here's a Boeing 777. These two aircraft classes have no explicit relationship to each other or to our original aircraft class beyond having identical interfaces to each other, with the exception of the initializer, which now takes fewer arguments. As such, we can use these new types in place of each other. Let's change our makeFlight method into makeFlights to use them. The different types of aircraft work fine when used with flight because they both quack like ducks, or fly like planes, or something. Duck typing and polymorphism is very important in Python. In fact, it's the basis for the collection protocols we discussed, such as iterator, iterable, and sequence.